Children, here let us see the applications of the Biot-Savart's law. We are going to find the magnetic field due to a circular loop carrying current using Biot-Savart's law. Okay, what will be the magnetic field due to a current carrying circular loop? And here we are calculating it, that is the magnetic field at a point on the axial line. So magnetic field due to a circular loop carrying current at a point on the axial line. So first you consider a current carrying loop. Loop means circle, which is having center at O. Its radius is given as small letter a. And a current I is passing through it in the direction as shown in figure. That is in the anti-clockwise direction, a current I is passing through the circular loop. We are going to find an expression for magnetic field at this point P. What will be the magnetic field at the point P due to this current carrying loop? We know the expression for the magnetic field due to a current element from Biot-Savart's law. So we are going to apply Biot-Savart's law. This point P is at a distance small letter x from the center of the current carrying loop. One more thing, the current carrying loop is kept perpendicular to the plane of diagram. In which plane we are drawing the diagram, the loop is kept perpendicular to that plane. Okay, that is, this is x-axis, this is y-axis, and this is z-axis. Therefore, we are drawing the figures in xy plane. In this plane, we are drawing the figures in xy plane. So the coil is kept in yz plane like this. This point you should keep in mind, that is, the coil is kept in a perpendicular direction to the plane. It is kept in yz plane. Therefore, at this point, the current will come out of the plane, and at this point, the current will go into the plane because the circular loop is kept in perpendicular direction. Clear? Now, let us consider a small element of the circular loop that is marked in red color here. Here it is marked in red color. And let us call it as XY. That small current element is XY. What we are going to do is, actually we have to find the magnetic field at P due to the circular loop. So we will cut the circular loop into a large number of small elements, dl, and we will find the magnetic field at P due to a single element. If we get the magnetic field due to a single element, we can find out the magnetic field due to the entire circular loop by integrating the result or by taking the summation. That is, we can find out the magnetic field due to each element. Then you add all the results. You will get the total magnetic field at P due to the entire circular loop. That is the procedure what we are going to follow. So first let us split the circular loop into a large number of elements and consider such an element, and it is named as xy. It is shown there in red color, and the distance of this xy from P, it is given as r. The distance of the element xy from the point P is given as r. Now the length of the small element xy is dl. The length of the small element xy is dl. Since it is a current element, it is having a direction, and in the previous class I have told you that the direction of dl, it is taken by drawing tangent. So to find the direction of this dl, here at this point xy, you draw a tangent. So here you can draw a tangent. The tangent may have either direction like this or the direction like this. So which direction you have to select is that you see the direction of current, and you have to select the direction of flow of current. In which direction the current is flowing here? Like this now. Therefore here the current is coming out of the plane. Therefore the direction of dl for the current element xy will be out of the plane. That is like this. Actually it is out of the plane because the circular loop is kept in a perpendicular direction. So you imagine it, a loop kept in a perpendicular direction, and on the top you imagine a small current element. You can see what will be the direction of that small element dl. It is out of the plane now. Therefore the angle between the dl is out of the plane and the distance r, this r, it is in xy plane. The distance r is in xy plane. Therefore the angle between dl and r will be 90 degree. That is shown there. The angle between dl, vector dl and r will be 90 degree. Now we are going to find the magnetic field due to this small element xy at the point P. First let us find out the direction of magnetic field. To find the magnitude of the magnetic field we can use Biot-Savart's law. What is Biot-Savart's law? dB equal to, or dB is equal to mu 0 by 4 pi I dl cross r divided by r cube. This is Biot-Savart's law. So using this equation we can find both the magnitude and direction. Let us find the direction of the magnetic field. You know, since this equation contains a cross product dl cross r, the direction of dB also will be the direction of dl cross r. The direction of dB, magnetic field dB, due to small element xy will be in the direction of dl cross r. So first let us find out the direction of dl cross r and mark the direction of dB in the figure. In the last class I have said that to find the direction of any cross product you can use the same palm rule. What is the palm rule? Stretch your thumb in the direction of first vector, all others finger in the direction of second vector, that is thumb in the direction of DL and all other fingers in the direction of R, then palm will point in the direction of DL cross R. Then you will get the direction of DL cross R. The same will be the direction of DB. Okay, so let us do it. You use your right hand. You keep in mind that the circular loop is in a perpendicular direction. And the direction of DL for XY, element XY is out of the plane. It will be out of the plane. Because at that point, if you draw a tangent, it will come out of the plane. So you use your right hand, stretch your thumb in the direction of DL, that is at the point of XY, you stretch your thumb out of the plane. Then stretch all other fingers just like R. Then see in which direction the palm points. This direction now. Yes. This is the direction of DL cross R and hence the direction of DB. So we have got the direction of magnetic field produced by not the entire circular loop but produced by a small current element XY. Now we can resolve this dB, this magnetic field, into two components as shown in the figure. That is, suppose this angle is phi, then the component near to phi will be dB cos phi and the other component will be dB sin phi. We are resolving dB into two components considering the angle of dB with the y-axis as phi. If you suppose the angle that dB makes with the y-axis is phi, which are the two components? The component near to the angle is cos phi component, that is dB cos phi, and other component will be dB sin phi. One more point is the direction of dB is the direction of DL cross R. Always this dB will be perpendicular to the plane containing DL and R. Already we have got the direction, but one more point is there. The dB will be always the plane containing DL and R. Then let us see which is the plane containing DL and R. DL is in outward direction. R is shown here in red color. Therefore, if you draw a plane like this, this will be the plane containing DL and R. Therefore, this dB will be perpendicular to this plane, which means this angle will be 90 degree. So we have got this angle is 90 degree, but we supposed this angle as theta. Therefore, this angle will be 90 minus theta, not theta phi. 90 minus phi. So this angle we got 90 minus phi. Now this angle also 90. Therefore, what will be this angle? This is 90 minus phi. Therefore, this angle will be phi. That is what marked there. Both the angles as phi. Next, so remember all these things. First, we considered a circular coil carrying a current I, which is kept in YZ plane, that is perpendicular to the plane of drawing. And we are going to find the magnetic field at the point P. To find the magnetic field, we cut the entire circular loop into a large number of small elements, and we considered a single element XY, and then we found out the direction of magnetic field due to this small element XY at the point P. And we resolved the dB into two components, dB cos phi and dB sin phi. Next, we can see another element known as x dash y dash just in the opposite side of the xy. Okay, here you can see at this point current is going into the plane. Therefore, the direction of dl and current both are same now. Therefore, the direction of dl is into the plane. At xy, it is out of the plane. Here it is into the plane. But it is having the same length as that of xy. We consider an element x dash y dash having the same length as that of xy. And this x dash y dash will be at the same distance from the point P, that is R. Therefore, actually xy and x dash y both are identical. Only one difference is that the direction of dl are different for both these elements. They are in opposite directions. Therefore, these two elements will produce same magnitude of magnetic field at the point P, but the direction of magnetic fields will be opposite because the direction of current is opposite in their case. Okay, therefore the direction of magnitude will be opposite for these two elements. Therefore, what will be the direction of magnetic field due to this element x dash y dash? It will be like this. Again, we can consider the angle that dB makes with the negative y-axis as phi, and then resolving dB into two components. Let us write like this. The component near to angle phi is dB cos phi, and the other component is dB sin phi. Now, actually we are going to find the magnetic field due to each small current element, that we will add all these magnetic fields to get the total magnetic field. Okay. For an example, let us add the magnetic field due to these two components only, xy and x dash y dash only. Let us add. Then we have to add the first dB and the second dB. Okay. Then instead of adding dB, we can add all the components only. Then you will get the same result. That is, to find the total magnetic field produced by the two components xy, two current elements xy and x dash y, how you will write dB plus dB. But how you can write dB? We have splitted dB into two components, dB cos phi and dB sin phi. And what about the other dB? It also split into two components, dB cos phi and dB sin phi. Therefore, instead of adding dB and dB, we can add all these four components. That is 2 dB sin phi components and 2 dB cos phi components. But what about dB cos phi components? These dB cos phi components have same magnitude because they are produced by identical current elements xy and x dash y dash. But their directions are opposite. Therefore, if you add cos phi components, you will get 0 because they are having equal magnitude but opposite directions. And what are remaining there? Only dB sin phi remaining there. Therefore, if you add dB plus dB, vector dB plus vector dB, you can write it is dB sin phi plus dB cos phi plus dB sin phi plus dB cos phi. But dB cos phi plus dB cos phi will become 0 as they have equal magnitude and opposite directions. Therefore, you will get only 2 times dB sin phi. This is the case. This is the total field produced by only 2 elements, current elements xy and x dash y dash. So, we have splitted the entire circular loop into a large number of current elements. And to find the total field due to the circular loop, we have to add all these magnetic field due to all the current elements. But if we consider any current element, small current element, we can see another element in just diametrically opposite side of it, such that these two elements will produce magnetic field in the opposite directions. Therefore, if you consider the components of these two magnetic fields, their cos phi components will be cancelled due to opposite directions. I think you got the idea now. So, when we add up all the magnetic fields, we have to consider only which component, sin phi components only, because the cos phi components of the magnetic field produced by all the small current elements will be cancelled out by diametrically opposite current element. All these are noted here. The plane of the coil is considered perpendicular to the plane of the diagram. It's already said there, such that the direction of magnetic field can be visualized on the plane of the diagram. At C and D, current elements xy and x dash y dash are considered such that current at C emerges out. It's already explained, For, current at C means at C it is the current element xy. The xy is at the point C, x dash y dash we considered at the point D. So for the xy, current is coming outside, and for x dash y dash, current is going into the plane. That is noted here. At D enters into the plane of the diagram. Now we are going to find the magnitude of magnetic field. The magnetic field due to a small current element xy of length dl is given as, by Biot-Savart's law. What is the magnetic field due to a small current element? Mu 0 by 4 pi IDL sin theta by r square. Okay, where theta is angle between DL and R. You see the figure, what is the angle between DL and R? It is 90 degree, no? Therefore, sin 90 is equal to 1. Therefore, dB is equal to mu 0 IDL by 4 pi R square. This is the magnitude of the magnetic field produced by the current element XY. The direction of dB is obtained using right hand rule and is shown in figure. We have seen the direction and we have explained everything there. dB is resolved into two components, dB cos phi and dB sin phi. Therefore, we can write dB is equal to dB sin phi I cap plus dB cos phi j cap. You see the figure, sin phi component is along x direction and cos phi component is along y direction. Since dB is a vector, we have to mention the direction of each component here. This equation is written just like we are writing 10 is equal to 6 plus 4. What is 10? It is 6 plus 4. Okay. Similarly, here dB is dB sin phi plus dB cos phi, but dB is a vector, therefore we have to mention the direction of each component. Sin phi component is along x direction and cos phi component is along y direction. That is why we added I cap and j cap there. Therefore, magnetic field due to the entire length of current element. So the magnetic field due to the circular loop, we have to find by adding all the magnetic fields, all the magnetic fields produced by small current element. That is B is equal to summation dB. Is equal to summation, what is dB? It is dB sin phi I cap plus dB cos phi j cap. Or putting sigma for each term separately, B is equal to sigma dB sin phi I cap plus sigma dB cos phi j cap. Now, in diametrically opposite side of current element xy, there is an element x dash y dash of same length dl. X dash y dash produces a magnetic field of same magnitude dB at P but in opposite direction. Due to diametrically opposite current elements, cos phi components are always opposite to each other and hence they cancel out each other. Sin phi components due to all current elements dl get added up along the same direction. So we know all the cos phi components will get cancelled, and if you take this sum of all the cos phi components, we will get 0. That is sigma dB cos phi is equal to 0. Therefore, our equation 2, it will become B is equal to 0 plus sigma dB sin phi I cap. That is sigma dB sin phi I cap. From the equation 1 we have, that is from Biot-Savart's law, we have the magnitude of dB, that is mu 0 I dl by 4 pi r square. Substituting the B is equal to sigma mu 0 I dl by 4 pi r square sin phi I cap. The sigma we can replace using integration. That is B is equal to integral mu 0 I dl 4 pi r square sin phi I cap. Now here integration is over which term? As dB is the magnetic field due to a small current element, we have to find out the magnetic field due to the entire current element. Therefore, we have to integrate dl, the term dl. Okay. Therefore, accept dl, bring all other term outside the integral. We can write mu 0 I divided by 4 pi r square sin phi I cap integral dl. So, what is integral dl? dl is a small length of the circular loop. Therefore, integral dl means the result we obtained after adding all the small current elements. Then if you add all the length of the small current elements, what you will get? The perimeter of the circle, that is 2 pi a. Therefore, integral dl is equal to 2 pi a. Moreover, here one more term is there, sin phi. From the diagram, you see the diagram. We can find a triangle there. From that triangle, what is sin phi? Opposite side divided by hypotenuse. What is opposite side there? A divided by r. Hypotenuse is r. Therefore, substituting these two values in the equation for B, we can write B is equal to mu 0 I by 4 pi r square, A by r, I cap 2 pi A. Or B is equal to mu 0 I 2 pi A square divided by 4 pi r square, r I cap, r square and r together will become r cube. Therefore, B is equal to mu 0 I 2 pi A square divided by 4 pi r cube I cap. Again, you see the triangle in the diagram. If we apply Pythagoras theorem, we can write r square is equal to a square plus x square, or r is equal to a square plus x square raised to 1 by 2. That is square root of a square plus x square. So r cube is equal to, actually it is r cube, no? r cube is equal to a square plus x square raised to 3 by 2. Therefore, instead of this r cube, what we can write? A square plus x square raised to 3 by 2 we can write. Therefore, this equation will become mu 0 I by 4 pi 2 pi a square plus x square raised to 3 by 2 I cap. Or in the numerator there is 2 pi, in the denominator there is 4 pi. Cancelling, finally we will get b is equal to mu 0 I a square divided by 2 a square plus x square raised to 3 by 2 I cap. This is the final result. This is the final result of the magnitude produced at the point P due to the entire circular loop. We can see the direction of magnetic field is along I cap. Okay. Now let us find the same what will be the magnetic field at the center of the loop. At the center, what is the value of that x? You see at the center means consider the point P is at the center. If the point P is at the center, x will be equal to 0. Then substituting x is equal to 0 in this equation, you can rewrite b is equal to mu 0 I a square by 2 a square plus 0 whole raised to 3 by 2. What is a square raised to 3 by 2? It is a cube. Therefore, in the numerator there is a square. In the denominator there is a cube. Cancelling all, you will get the final result as mu 0 I by 2a I cap. That is at the center of the loop. Then some special cases we can see here. The first case is already explained, that is at the center of the loop. We got this result at the center of the loop. And the second case is if the observation point is far away from the coil, then we can take the approximation a is very much less than x. So in the third equation, we can neglect a square. So we will get the result as, if you neglect a square in the third equation, that is the term a square in the denominator of the third equation, we will get the equation like this. If the field point is far away from the coil. And this equation, it is clear that B is inversely proportional to 1 by x cube. B is inversely proportional to 1 by x cube. So how we can draw the graph? If you draw a graph B versus x, let us draw like this. Okay. Since B is proportional to 1 by x cube. Next, in the case of a current carrying loop, we can find out the direction of magnetic field using another right hand rule. You know, in the direction of a straight conductor, how you will find the magnetic field? Stretch your thumb in the direction of current, then curl the fingers around the conductor, then curling fingers will give you the direction of magnetic field. Okay, that is the direction of magnetic field due to a straight current carrying conductor. A reverse case we can use in the case of a current carrying coil. That is, in the case of a current carrying coil, you curl your fingers of right hand in the direction of current. Curl the fingers of right hand in the direction of current. Then stretched thumb will give you the direction of magnetic field. You can see here. This is a current carrying loop. You can see current is flowing clockwise direction. Then you use your right hand and curl your fingers in the right hand fingers of which one? Right hand in the clockwise direction, and see in this direction your thumb points into the plane. No? There will be the direction of magnetic field. And you know magnetic field forms closed loop, therefore they will form closed loops like this. They will be into the plane and they will form closed loops like this. Here it is clean very clearly. If the current is flowing anti-clockwise direction, the magnetic field will be like this. You can see your stretched thumb will point like this, and here it will form closed loop like this.